China just turned on a machine that engineers said was impossible to build for over 60 years. It is called a supercritical carbon dioxide turbine, and it just went live on a real power grid for the first time in human history. Not in a lab, not in a research paper, on an actual grid, making actual electricity, right now. The numbers are almost hard to say out loud. This machine can hit 50% efficiency, compared to the 35% ceiling that steam turbines have been stuck at for over a century. It does this in a package that is a fraction of the size. And it does not use a single drop of water to do it. Instead, it runs on the same gas that comes out of your lungs every time you exhale. This is not a small tweak to an old machine. This is a direct challenge to the steam turbine, a piece of technology that has sat at the center of global power generation for more than 140 years. Before we get into what China actually built, hit subscribe now so you do not miss where this goes, because by the end of this video you are going to understand why almost every power plant on Earth is quietly wasting more energy than it uses. Think about your electricity for a second. Coal, gas, nuclear, even some solar setups. It almost always ends the same way. Water gets heated into steam. The steam blasts through a giant wheel of blades. The wheel spins. The spin becomes electricity. That is the entire system. It is the same basic idea from the 1800s, just dressed up with better metals and hotter fires. Here is the part that stings. Even the best steam turbines in the world today only convert about 35% of their heat into usable electricity. The other 65% just disappears, vented into the sky or dumped into a river as waste warmth. More than half the energy the world burns never even makes it to your wall out. Scientists have known this for decades. Raise that number from 35% to even 45 or 50%, and the math changes everything. Less fuel burned, less pollution, billions saved. The idea was never the hard part. Building it was. You learned 3 states of matter in school: solid, liquid, gas. But there is a 4th one, and it is the whole secret behind this new machine. Push a substance hard enough on both temperature and pressure at once, and something strange happens. The line between liquid and gas disappears. It becomes something in between, dense like a liquid, flowing like a gas. Scientists call it a supercritical fluid. Water needs brutal conditions to get there. 374 degrees Celsius and 220 atmospheres of pressure. That is punishing on machinery and expensive to sustain. Carbon dioxide reaches the same state at just 31 degrees Celsius and about 70 atmospheres. That is a warm afternoon and a manageable amount of pressure. Suddenly, this exotic state of matter is not some far-off lab curiosity. It is almost easy to reach, and once carbon dioxide crosses into that state, it becomes nearly as dense as water while still flowing like a gas through pipes and turbines. That combination is exactly what a power plant wants. More mass moving through the blades every second means more power out, and it means the whole machine can shrink dramatically. Smaller blades, smaller pipes, smaller footprint, less waste. Quick reminder to smash that subscribe button if this is blowing your mind a little, because it is about to get even crazier. If the physics is this clean, why did the world wait until now? Because building it is brutal. To get real performance, the carbon dioxide has to be heated to roughly 700 degrees Celsius before it even enters the turbine. At that temperature, most metals slowly deform under load, a process engineers call creep. Add in the fact that hot, pressurized carbon dioxide actually forces carbon atoms into certain metals over time, making them brittle from the inside out. A brittle blade spinning at tens of thousands of RPM is not a small risk. It is a catastrophic one. Then there is the heat exchanger, arguably the hardest part of the entire system. To hit these efficiency numbers, the machine has to recycle heat from its own exhaust back into the incoming flow, through walls thinner than anything else in the power industry, all while both sides sit under roughly 200 atmospheres of pressure. Engineers etch channels finer than a human hair into metal plates and fuse thousands of them into a single solid block. It cannot be opened. It cannot be easily inspected. One hidden crack under that kind of pressure is a serious problem. And then there is speed. A smaller turbine has to spin faster to produce the same power, often tens of thousands of RPM. Normal oil bearings would cook themselves within hours at that speed, so engineers had to invent entirely new bearing systems, some using magnetic levitation, some floating on a thin cushion of the carbon dioxide itself. Both work. Neither has decades of real-world proof behind it. Stack all of that together, and you start to understand why 60+ years of research across multiple countries never produced a grid-connected system. Until now, in late 2025, engineers connected two supercritical CO₂ turbines to a real power grid at a steel plant, each rated at 15 megawatts, forming a combined system the world is now watching closely. This is the first time this technology has ever run on a commercial grid. The system does not burn its own fuel. It captures the waste heat a steel plant was already venting into the atmosphere and turns it into usable electricity. Compared to the steam turbine it replaced, it produces roughly 50% more electricity from the exact same heat source, in about half the physical footprint, with heat recovery efficiency jumping dramatically. Over a full year, that translates into tens of millions of kilowatt hours pulled from heat that used to simply vanish, worth millions of dollars in extra revenue, from a factory that changed nothing about how it makes steel. The only difference is a smarter machine sitting in the loop, catching value that used to be thrown away. If you are enjoying this breakdown, this is exactly the kind of story we cover every week. So go ahead and subscribe now so the next one lands in your feed. Here is the honest part. This is not being installed at a nuclear plant. It is not the primary turbine in a major coal or gas facility. It is sitting in a waste heat loop at a steel factory, which is about the lowest stakes place you could test this technology. If something goes wrong, the factory just makes a little less bonus power. Nothing critical goes dark. That is not a weakness, it is a strategy. Before anyone trusts this system inside a nuclear reactor or a major grid plant, it needs years of real operating data. Bearings need more hours. Heat exchangers need to prove they can survive decades without a hidden crack. None of that data existed before this system started running, and now, every single hour it operates, that data is being created. If engineers can scale the materials and manufacturing to handle this reliably, the implications are massive. Smaller nuclear reactors, factories quietly turning waste heat into profit, power systems compact enough to fit on a ship, solar plants that work in dry regions where steam cooling was never an option. The United States, Germany, South Korea, and Japan all have research programs chasing the same goal. But China just became the first to move from research paper to real grid. In technology, that kind of head start tends to compound. The steam cycle was described in 1859. The supercritical CO₂ cycle was described in 1872. After more than a century of chasing the same finish line, the newer idea is finally pulling ahead by about 13 years of physics history. Sometimes, that is all it takes to change everything. So here is the question. If this technology becomes the new standard, which industry wins the most? Nuclear, steel, shipping, or something nobody's talking about yet? Drop your answer in the comments. And if you want to catch the next breakdown the moment it goes live, make sure you are subscribed.